In lecture 10, we are going to study the photo-induced kinetics of photochemical reactions. So at first, let's remind you how fast light propagate, depending on the time scale you are thinking about. So please just calculate how long can light propagate for 1 second, millisecond, microsecond, and 1 nanosecond, meaning the 10 to the minus 9th, and the picosecond, which is 10 to the minus 12th, and femtosecond, which is 10 to the minus 15th second. Okay. Then, so as you know that for 1 second, light can propagate for the distance equal to the 7th round of the Earth. Right? So it's a very huge distance, and which is 3 times 10 to the 8 meter. And of course, every step you have to multiply 10 to the minus 3. So it could be in 1 millisecond, 10 to the 5/5, and then it's too big and to imagine it's like 300 kilometers. And on the microsecond, it's about so 300 meters. So it's like the 1 round of the athletic ground, and roughly in 1 nanosecond, it's 0.3 meter, which is 30 centimeter. So meaning that it's same as the linear ruler you used to use. And on 1 second, it's 0.3 times 10 to the minus 3 meter, which is equal to 300 micron. So it's quite tiny, but you still can recognize the distance, right? So it's less than 1 millimeter. And now for femtosecond, it's like 0.3 micron, so which is 300 nanometer. Now very small, and probably you cannot recognize the distance. So this is a length you are thinking about when we think about the time scale shown here. Let me remind you that the photoreactions start from femtosecond order after light is absorbed by molecules. As I mentioned before, the wavelength is quite long, right? So it's like order of the less than 1 micron order. But compared with some sort of the molecule, which is on the order of angstrom level, which is less than 1 nanometer, so this wavelength is still very big. And then this wave propagate through the molecule start to light absorption, and then the photoreaction start. So this is the starting point of the photochemical reaction. Okay. Then what will happen for next is kind of summarized in a drawing called Jablonski Diagram. The photochemical process is summarized in a drawing called the Jablonski Diagram, which is the summary of various photochemical photo-induced processes in a single diagram, which is shown here. So it's a very simplified Jablonski diagram, but you could understand various photochemical processes after photo excitation. So let's see, this is absorption. So absorption start from the ground excited state, the vibrational ground state, and also electronic the ground state. And then it's go up there, and as you run, it's going to the vibrational excited state of the excited state, right? So there's some extra energy for this. So this corresponds to the vibrational energy. So this decay, this is a vibrational relaxation. And which gives the heat. So thermal relaxation. And from the bottom of here, you have two processes from S1 process. The one is light emitting, which is called the fluorescence. And also there's some thermal decay. So as I didn't show you the vibrational energy level between the S0 and S1, but always there are many another the small energy level, and using this kind of thermal relaxation process, using the vibrational motion, rotational motion, so energy is gradually lost by the motion. This is called this is thermal energy, so it's internal conversion. And also there's some important process in photochemistry, which is the transfer from the S1 state to T1 state, which is called inter-system crossing. Inter-system crossing, right? And also that's why you could obtain not only the singlet state, but also you could obtain the triplet state, triplet excited state. So after the molecules become the higher energy level of triplet state, so again it needs to release the energy by heat, which is the same as the S1 case. It's vibrational relaxation. And similarly, after reaching the vibrational ground state of T1, there are two processes, and one is light emitting, and the other is thermal release. And the thermal release one, this is the same, so it is called internal conversion. But the light emitting process, this is called phosphorescence. Okay, so here is a kind of the diagram which shows various for the photo-induced processes. Okay, and these processes, the time scale for these processes are summarized in the right figure. So as I mentioned, this is 10 to the minus 15th, which is the light absorption process. So very fast process. So this is the initial process. And around this time, initially the if the molecules are in a solution, the solvent molecules move around to organize the optimize the structure, which is a solvent motion. And also at the initial process, the electron or proton transfer happened on the order of femsecond to picosecond order. And also the origin of chemical reaction, which is a dissociation bond, could happen on the order of the picosecond, femsecond, picosecond order. Because as you see, we'll understand this part later on, but it is related to the vibrational motion of the molecules. And also the molecules are rotating or translated. So it's basically motion process happens on the after a picosecond order. And also the chemical process, like chemical reaction, also from the picosecond order to, so depending on the chemical reaction, this takes in a very wide time range order. On the other hand, people sometimes use the fluorescence and phosphorescence process. And because it's light emitting processes, we could use the light, use them for some detection of chemicals or kinetic analysis. And this process is on the order of fluorescence part. The light emitting process from S1 state is on the order of nanosecond. On the other hand, phosphorescence process, which is the light emitting from a triplet state, which is much slower, on the microsecond and even extending into the millisecond order. So this is the time scale we are thinking about in photochemical processes.